Okay, so this video is our part 2 of our Unit 3 study guide before we take our Unit 3 exam. We're starting off on numbers 16 through 19 where we are supposed to convert each of these quadratic functions to vertex form. Right now we're in standard form. We're almost in like what we could call ABC order. X squared, then our x, then our constant. Okay, that would be our a, b, and then c values. Arranged like that. By looking at this equation, I cannot tell what the vertex is. So I want to just show the same exact equation in a different way. And in class, we kind of talked about that this is like using a different language, like saying hello or hola or aloha. Okay, those are all different ways of saying the same phrase. They mean the same thing. So I'm not going to change this from being really x squared minus 16x plus 64. I'm not going to change what that graph looks like, but I'm going to change how we show it with its equation. Okay, so this method is converting to vertex form by completing the square. So when you're doing this, if you didn't recognize that we had a perfect square trinomial already, step 1 for your 5-step process, and this is from lesson 3.6, it says to make a grouping out of your x squared and your x term. So we kicked out the constant. What we're trying to build inside the parentheses is a perfect square trinomial. Okay, then you would check, what do you have in front of x squared? Do you have a number or like a negative sign, anything in front of x squared? If you did, you would have to divide it out of both terms in parentheses. We don't have anything in front of x squared, so we kind of get to skip that step for this problem. Next, we look at our b value. Okay, our b value is a number that's always in front of x, which is negative 16. So you take your b value and it says take half of it, which means divide it by 2. So we have negative 8. After that, it says, and then square it. So that means we're going to put parentheses around it and square it. What that means is we have negative 8 times negative 8, which makes positive 64. This value, it's our new c, should always be positive. Now what we're going to do is we are rebuilding what we had up here. We want a third term. We want to make it a trinomial inside the parentheses. So we're going to rebuild what we had. We had x squared minus 16x. And we're going to say plus, and I'm going to label it as like a box. That's going to be where our new c value goes. We had a plus 64 on the outside of the parentheses from above, but to keep this balanced, we have to subtract what we had added inside the parentheses. And we're going to call this a times c, but since our a value is 1, it is the same as our c value. So what goes in the parentheses? Again, this box right here is for the c value, so 64 goes here. I would do 64 times my a value, which is 1. It's going to stay 64. That goes in the outside box. Okay, now I have a trinomial inside. I have 1, 2, 3. I can do my factor tree. What multiplies to positive 64 and adds to negative 16? Well, we always have a very nice clue here. It's always going to be half of our b value, which is awesome. So it's going to be negative 8 and negative 8. Now this could be written as x minus 8 times x minus 8 if we're showing it in factored form, but that still doesn't look like vertex form. Because I have 2 of the same identical factors, I can write this as x minus 8 in parentheses all being squared. Squared means I have 2 of those factors. And then I just compute what I had on the outside. I had 64 minus 64, which is 0. Okay, so I don't need to put anything down here. We're going to finish it off by putting f of x equals x minus 8 all being squared. Now this is in vertex form. It is the same as the above equation, but from this expression of it, I can tell what the vertex is. The vertex would be positive 8 for x, 0 for y. And that's why we like vertex form. Okay, so moving on to number 17, we're doing the same 5-step process every time we're asked to convert to vertex form. So I'm going to start. I have x squared plus 2x minus 8. I'm going to put parentheses around my x values, kicking the constant on the outside. I'm looking, do I have a number in front of x squared? I don't, so we don't have to worry about dividing. I'm going to take my b value, which is 2. I'm going to divide it by 2, which equals 1. And then we have to square it. 1 times 1 is still 1. This again is my new c value. So we're going to take what we had above. We want to add a third term inside the parentheses so we can do our 1, 2, 3 factor tree. So we have x squared plus 2x, and I'm going to say plus my box, close the parentheses, have minus 8, and I'm going to say minus. It's always minus on the outside, a times c. So in the box, inside 1, it's always at half of b value squared, 1. 1, I'm checking out here. If I had a number, I would multiply that c value by it. I don't have one, so it's going to stay 1. Now we're ready to factor. What multiplies to positive 1 and adds to positive 2? Those same two numbers, because we do want a perfect square here, would be 1 and 1. They multiply to 1, they add to 2. So instead of saying x plus 1 times x plus 1, I'm going to say that we have x plus 1 squared. We had 2 of those factors. And negative 8 minus 1 is negative 9. So our function is equal to x plus 1 squared minus 9. And from here we know that the vertex would be negative 1 for x, negative 9 for y. Okay, number 18, we have the function negative x squared plus 10x minus 23. This is in standard form. We want to make it in vertex form. So we're going to start by making a grouping out of negative x squared plus 10x. Now I'm looking in front of x squared, checking to see if there's anything there. I have a negative sign that I need to pull that to the outside of the parentheses. I do that by dividing by whatever that is. That's a negative 1 to both terms inside. So negative x squared divided by negative 1 becomes positive x squared. Positive 10x divided by negative 1 is negative 10x. Okay, then we put the parentheses back around. But that negative 1 we pulled out has to go on the outside of the parentheses. And then we just bring down that minus 23 that we had kicked out on the outside. So now you can see that our b value is negative 10. We're going to divide that by 2. We're taking half of it, which equals negative 5. Then we wrap it in parentheses and we square it, and that makes a positive 25, which is our new c value. So we're going to rebuild what we had above that. We have negative 1 on the outside, or just a negative sign, however you would like. We have x squared minus 10x, and we're going to say plus our box, which is our c value. Close it. And then we had negative 23, and we're going to say minus our box, which is a times c. Okay, so now what's going on the inside box is positive 25, and we like this because it made us a perfect square trinomial. What goes in the outside box is a times c. So we have this 25 gets multiplied by the negative 1 that's on the outside. That's our a value. So 25 times negative 1 is negative 25. Okay, now again, we're going to be focused right now on what's inside the parentheses. We have a perfect square trinomial. 1, 2, 3, we want to use our factor tree to get this to a factor, what goes in the parentheses. We want to know what multiplies a positive 25 but adds to negative 10. Again, it's always going to be half of our b value. Negative 5 times negative 5. That does make positive 25 and does add to negative 10. So we're going to rewrite this. We have a negative on the outside. We have x minus 5 in our parentheses. We are going to square that because we had 2 x minus 5s as our factor. Then we put together what's outside the parentheses. Negative 23 minus negative 25. We have a double negative, which really means to add. So negative 23 plus 25 is positive 2. We're going to throw f of x in front of it, and we have our function in vertex form. Negative and then x minus 5 squared plus 2. Our vertex, we can see now, is positive 5 for x, positive 2 for y. Okay, that leads us into number 19. Okay, we have negative 2x squared plus 12x minus 19 that we want to convert to vertex form as well. Start by making that grouping of the negative 2x squared plus 12x. I'm looking in front of x squared. I have a negative 2. Can't have anything in front of x squared. So whatever is in front of x squared, we divide it out of both of those terms. So negative 2x squared divided by negative 2 leaves us with positive x squared. 12 divided by negative 2 is negative 6x. Put the parentheses back around it, and that number is just now pulled out to the front of the parentheses. Bring down the negative 19. So our b value now is negative 6. So we're going to take that negative 6, we're going to take half of it, which gives us negative 3, and then we're going to square it, which it becomes positive 9. Your new c will always be positive. We take what we had above, and we're going to rewrite it as negative 2 x squared minus 6x plus our box, which is our c value, our new c value. We had a minus 19 on the outside, and we're going to say minus our box, which is a times c. So what's going in our box? The inside box gets 9. It's always that same exact number we had just found. What goes into our outside box? This 9 times the a value, which is -2. So 9 times -2 is -18. We got that double negative situation happening again. Okay, after we've done that, we have 1, 2, 3 terms inside. We're ready to do our factor tree. What multiplies to 9 but adds to -6 is going to be -3 times -3. So our in factored form, we'd be -2 parentheses x minus 3 squared, because there's two -3 factors. On the outside, we have -19 minus -18, which really means to add 18, which adds to -1. So we would have f of x equals -2 times x minus 3 squared, subtracting 1, which shows me that the vertex is at +3, -1. Okay, so that's converting to vertex form by completing the square. Okay, in this next section, we are graphing piecewise functions, and this is the section that you all just hated so much. And I keep trying to think of ways to make you not hate it so much. Haven't thought of that yet, but we'll just give it another try. Hopefully, we're all getting better at this. I have two different equations. My two different equations are, we have 2x plus 7, and we also have -1/4 x. Okay. Now, those are both linear equations that you know how to graph, but we don't want to graph the whole equation for each of these lines. We only want to graph a piece of them. So what's to the right of each equation is telling us which x's we are allowed to plug in for these equations. Okay, so we're going to show that with a table of values. So we kind of have a cutoff point where this is happening, where it says x is less than -4 for 2x plus 7, and x is greater than or equal to -4 for our equation -1/4 x. What that does is it generates like a starting place where each of the pieces is going to originate from and move in opposite directions from. So where x is -4. Ooh, 1, 2, 3, 4. Right here, we put a vertical wall. It's kind of like the Berlin Wall. We cannot cross it. Each of these lines starts there but moves in opposite directions. They cannot overlap. It's not allowed. They'll get like shot. Berlin Wall. Okay. So for my equation, we have y equals, do it in green, 2x plus 7. Okay, when we're graphing, a lot of times, I feel like most of you, it makes sense to create a table of values. We're starting with the first x given, -4. Now you can think of it two ways. We're working with numbers to the left, less than -4, which would be like -5, -6, -7, and so on. Again, two ways that you can plug in 2x plus 7 into your graphing calculator and then go to your table of values from there, and then you're going to match. What does it say y is when x is -4, when x is -5, and so on. You have to make sure you're only using those values that it said up here where x is less than -4. Or you can plug them in by hand. Okay, what that means, I could do 2 times -4 plus 7. That'd be -8 plus 7, which equals -1. Okay, so when x is -4, y is -1. And you could keep going from there. What is y when x is -5? That'd be 2 times -5, which is -10, plus 7, which is -3. When we plug in -6, we would get -5. And when we plug in -7, we get -7. Okay, now we want to graph just this piece of the line. Okay, now my first point that I did, -4, -1, is going to be on this yellow wall that I created. And just for that circle, because it's on the wall and it will overlap with our other line just a little bit, we have to decide, is it going to be an open circle or a closed circle? Because it has just a less than sign, not less than or equal to, it will be open circle at -4, -1 right here. And then we have -5 and -3. Okay, we're moving down. And then we have -6, -5, and -7, -7. And we'll connect our points. Again, the whole line, would continue with the same slope to the right side like this, but we're not allowed to show all of that. This is the only piece we are allowed to graph. Now I'm going to work on my next piece. My next equation was y equals -1/4 x. Okay, so I create a table of values, and this piece right here is telling me which x's we can plug into our table. We can start with -4, and we're moving to the right of -4, or numbers bigger than -4, which are -3, -2, -1, 0, and so on. So if I plug in -4 for x, I would have -1/4 times -4, which equals +1. So we'll write that down on our table. Okay, then we could keep moving from there, or you could use your graphing calculator. When x is -3, we get 3/4. Okay, I'm going to write it down. Doesn't mean I have to plot that point. When x is -2, we get 1/2. When x is -1, we get 1/4. Again, I don't really like any of these, but when we get to x is 0, we know that y is 0. So I can see like, I don't like graphing fractions. We don't have to graph those points just because we put them on our table of values. I could keep looking at my table of values and I could see that the next y value, that's a whole number, would be when x is 4, y is -1. Okay, so you can kind of just plot the whole number points. But before you do that, go back to your first, where your first dot would be. That's going to be on the wall. We have -4, 1. Now go back to where it had it at the top. We say greater than or equal to. If it says or equal to, we're making a closed circle at that point. -4, +1, right here. And then I know I'm going to have 0, 0, and then 4, -1. So this is the piece of the line, and that was really wiggly, but that we are allowed to graph for this equation. Okay, so now that's it, but now we got to talk about domain and range. So we have at the wall, we're moving to the left forever from the wall and to the right forever from the wall. But we have to check. We may have an interruption to the domain or the x values that we are allowed to use. And that would happen at the wall where we're starting from. Are we equal to this -4 value for x? If we have closed and open, we are equal. Another way to look at it is the signs. If one of these has an or equal to bar, that means we do include the value at the wall, which means our domain will be all real numbers. Our range, okay, look for a highest or a lowest point, just like we always do. I feel like that's a good way to start. I have a highest point right here, which is 1. Now, I would kind of do my pencil test. I'm going to put my pencil like right here, and I'm going to move it downwards. As I move it downwards, am I always touching at least just one of those lines? And I always am. I do not have a hole or a gap in between my blue line and my green line because my green line fits inside the blue line's range as it's moving downwards. So no gap. We just have a highest point of 1, and we have all y values that are underneath that point. So we would write that as all the y's such that y is less than or equal to +1. Okay, number 21 is another piecewise function. We have negative absolute value of x plus 2 if the x's we are using or plugging into the equation are less than 1. We also have y equals 3x minus 5 if the x's we're plugging in are greater than 1. So we are going to just start with our top equation here. Okay, I'm also going to make my wall here. I have a wall where my x, why did that move? Where my x values, okay, are at, and that's going to be at +1 for x. So I'll kind of put that in just so I know that's where my values are going to originate and then move outwards in opposite directions from. So my first equation, we have negative y is equal to negative absolute value of x plus 2. We're making a table of values. You start your x with the value that comes after x, 1. Less than 1 would be 0, -1, -2, -3. This absolute value, I'm going to do kind of a few more just to get a feel of it. If we plug in 1 for x, we get 1 plus 2, which is 3. It comes out and it's going to turn negative, so we get -3. When we plug in 0, we get -2. When we plug in -1, -1 plus 2 is 1, and then it goes to -1. When we plug in -2, we are going to get 0. When -3 is plugged in, we get -1. And when -4 is plugged in, we get -4 plus 2, which is -2. Comes out as +2, but then turns negative again. So really, what do we have? We should have expected this. This is where our vertex is, but we don't get to make the whole V here because this is piecewise. We're only going to have a piece of our V. I'm going to look at my first point. Do I have an open or closed circle at 1, -3 on the wall? It's going to be open because it said just less than 1, not or equal to. So at 1, we are -3. 1, 2, 3 down. Open circle. Then we're at 0, -2. We went up. We're at -1, -1. That's still moving up. And -2, 0. Okay, and I knew that was my vertex. I recognized that because I had symmetry on either side of that point. So now we're going to start working our way down. -3, -1, -4, -2, and it would continue in this pattern as we move to the right. So you can see really good shape of the V. We just didn't get to make the whole right side of it. But my arrow does continue onward to the left. Okay, now we're going to look at my second piece, which is y equals 3x minus 5 for x's that are greater than 1. So y equals 3x minus 5. New table of values because it's a new equation. We're going to start with 1. Notice they both start with the same number, and we're greater than 1, 2, 3, 4, and so on. When we plug in 1, we get 3 times 1 is 3 minus 5 is -2. When we plug in 2, we get 3 times 2 is 6 minus 5, which is 1. We plug in 3, we get 4, and when we plug in 4 for x, 3 times 4 is 12 minus 5 is 7. Okay, that should be enough points for now. Looking at the first dot I'll make on the wall, 1, -2, is it open or closed? Again, this is just a greater than, not or equal to, so this one's open as well. So 1 and -2. So they're pretty close together. And then we have 2 and +1, and 3 and +1, 2, 3, 4, and 4 and 7. So this one has a pretty steep slope. Start here, and we're going up forever. Okay, our domain. Really, it comes down to checking where we are at the wall. Can we equal +1 for x, or are we never equal to +1? We just get really, really close to it. Because it's 2 open circles, we are not equal. Another way to check is look here. One was greater than, one was less than. Neither had an or equal to bar. So we would write that as, these are all the x's. Okay, we're moving outwards from the wall forever, left to right. But we have an interruption at 1 for x. So all the x's such that x cannot ever equal +1. Okay, my range. Notice, okay, my blue one is going up forever. My red one is going down forever. We have the potential for all real numbers. I'm just checking, do I have any gaps? Now you might think that right here we have a gap, but we don't. Look how I overlap with my red line. If I start at the bottom and worked my way up, I'm always touching one of these lines, and that's telling me that we have a range of all real numbers. We will get every y value covered here as we move from bottom to top. Okay, 22, we have p of x is equal to 5 if the x's we're using are less than or equal to 0. We are also p of x is equal to -x squared plus 3 if the x's we're using are greater than 0. So this one might be a little bit quicker for us. We're using basically y equals 5. If I make a table of values, I'm starting with 0 for x, 0, and less than 0 is -1, -2, -3, and so on. But notice this is just y equals 5. That means all the y's in this column have to be the same number, 5. There's no x to make it vary, okay, or change. So we are going to get a horizontal line. Now what will this first line or dot be? At 0, 5, well, it says less than or equal to, so that means we will have a closed circle there. Now let's put our wall in. I didn't do that yet, but our wall is going to be at 0, 0. Not 0, 0, but at 0, right here. They both were 0 is what I was trying to say. So my first circle will be at 0, +5, 1, 2, 3, 4, 5, and it is closed. So I'm going to fill that in. When x is -1, notice I'm working to the left. Your first line is always on the left, and then so forth. These are all +5 as we move more negative numbers for x. So that's my first piece that I get to graph. Now my second equation, we're doing -x squared plus 3. Two things I know just by looking at. Squared means it's a parabola. The negative sign means that the arrow should be ending going down. Those are things I know already. Okay, but we have y equals -x squared plus 3. We're making a table of values. The first x we plug in is 0, and then we're plugging in numbers greater. So 1, 2, 3, and so on. Okay, if I'm looking at my table of values and I plugged in 0, Well, negative 0 squared plus 3 is going to be positive 3. If I plug in 1, I have 1 squared is 1 times negative 1 is negative 1 plus 3 is 2. When we plug in 2, we're going to get negative 1, and we plug in 3, we have 3 squared is 9, becomes negative 9 plus 3, which is going to be negative 6. Okay, check your first circle, 0, 3. Here, up here, it shows that x can just be greater than 0, not or equal to, so this will be an open circle at 0, 1, 2, 3. Open circle. When x is 1, y is 2. When x is 2, y is negative 1, and 3, negative 6. So notice we're not getting the whole parabola here, but we're getting a part of it, a piece of it, piecewise. So our domain, what are we checking? We're checking, are we equal to the value at the wall? Are we going to be all real numbers, or are we going to be x does not equal 0? Closed and open means we are equal, or you could look, this one said or equal to. So if it's or equal to it, that means we include it. So our domain is all real numbers. My range, okay. Notice my yellow line, it's only at 5 for x, or for the y values. Okay, it's only here. Now my green line, it's starting at positive 3 and it's underneath. I have this gap. I have a true gap. See, everything I'm highlighting, I never have a yellow line or my green line in there. So that's a gap. I'm going to have a union because I have two separate ranges. How do I write that? Okay, let me get my pen to work. Maybe it will. Here we go. We are going to say that we have all the y's such that for my yellow line, y is always equal to 5. It's not going above 5 or below 5 for that yellow line. Stays there. Then we're going to union it, and my green line, my y's are starting at 3 and we're going below 3. And for this one, I'm not going to say or equal to because we had an open circle at that y value. There we go. Okay, on number 23, we have 3 different equations that we're going to graph pieces of. So we're going to have 2 walls and lines in 3 different sections. So notice we have h of x is equal to negative x minus 9 if the x's we're using are less than negative 2. That's a linear equation. That's going to be a diagonal line. Then we have x plus 1 minus 5. This is going to be in our middle section. Notice it's in the middle of all this business. For the x's that are between negative 2 and positive 2. And then we have 2 times x, the absolute value of x minus 3. That's going to be absolute value, or v-shaped, for the x's that are greater than or equal to 2. So we've got 3 different tables we're working with. Okay, so my first one, y is equal to negative x minus 9. Let's make a table for this equation. We're starting at negative 2, and we're less than that. So negative 3, negative 4, negative 5, and so on. So when we say plug in negative 2, we get negative negative 2, which turns into positive 2, and 2 minus 9 is negative 7, and we're going to keep going. Okay, when we plug in negative 3 for x, we're going to get negative 6 for y. When negative 4 is plugged in for x, again, this is the x I'm talking about, we're going to get negative 5. And when negative 5 is plugged in, we get negative 4. Again, check your first circle. Negative 2, negative 7, check the sign that was in there. I'm looking at where I have highlighted in red. It's just less than, not or equal to, so that will be open. So let's go to graph. First, I'm going to put my walls in. I have 2 walls, one at negative 2, one at positive 2. So here's negative 2's wall and positive 2. Graphs in each section. Again, I can kind of color code this. My red line will be in this section, my blue line will be in the middle section, and my green line will be in the last section. Okay, so negative 2, negative 7. So going down here. And I said open circle. Then we were at negative 3, negative 6, and negative 4, negative 5, and negative 5, negative 4. So this was our linear piece. Okay, has a constant slope headed that direction. Now I'm going to graph my blue line. I do know that it's part quadratic. I'm going to have part of a parabola here. I'm going to make a new table of values. Okay, this is for my x plus 1 squared minus 5. Again, this tells me I'm starting with negative 2. I have to end at positive 2. What numbers are in between there? We have -1, 0, 1, and then 2. So if we plugged in this to our calculator, okay, starting at -2, when x is -2, y is -4. When x is -1, y is -5, and that is the vertex from above. Okay, those numbers made my vertex, but notice I'm not getting a whole symmetrical piece of it. When x is 0, I get -4 again. I have that symmetry because that was my vertex previous. When x is 1, y is -1, and when x is 2, y is 4. So we check both of these, okay, the first and the last, they're both on the wall. When x is -2, that first one, and y is -4, this had an or equal to bar by that x. So this one's going to be closed, but at 2, 4, look right here, it's just less than 2. So this one's open. They can be different from each other. So we're at -2, -4, closed, and then we're at -1, -5. We went down to the vertex, then 0, -4, back up, 1, -1 is here, and then at 2 and +4, open circle. So it's just that piece of the parabola from -2 to +2. Okay, my last section, we have our graph that's going to be for 2 times the absolute value of x minus 3. Okay, table of values. Where are we starting for x? We're starting for 2, and we're getting larger than 2 because we're on the right side. So 2, 3, 4, 5, and so forth. So when x is 2, y is going to be 2. Okay. When x is 3, we have 3 minus 3 inside. 3 minus 3 is going to be 0. So 2 times 0 is still 0. When we plug in 4, we have 4 minus 3 is 1. 1 times 2 is 2. So again, we should have known too that 3, 0 was our vertex. But if you didn't recognize it, you should have noticed it when we started repeating values. When we plug in 5, we have 5 minus 3 is 2. 2 times 2 is 4. So we're going to have just a part of this v. We're at 2, 2. Now this first circle, it's going to be closed because it said or equal to 2. So we're at 2, 2, closed circle. Then we're at 3, 0. We go down, and now we're going to go back up. 4, 2, and 5, 4, and we would keep going up at a steady slope, just like this. Oh, I love it. Looks great. We will not probably have one this complicated on the test, but it's really fun to do in our notes. Okay, what is our domain? Check both of our walls at this point. Okay, we are equal to -2 because we had open or closed, or we can notice that we said or equal to -2. We are equal as well to +2 because we had another or equal to sign there. So because we're equal to those two values at the wall, our domain is all real numbers. Now, what about our range? Do we have a highest or lowest point? Notice we won't ever have a highest point because these arrows here are headed up forever. So my lowest point is going to be down here at -7. Okay, now as I move upwards, kind of your pencil test. Okay, I'm starting right here at -7. I'm moving up, and I'm always touching at least one of those lines, so I don't have any gaps on this one. So this is a pretty normal range, even though there's a lot of lines. All the y such that y is greater than or equal to -7. And that's it for our piecewise. Okay, so numbers 24 through 28 go along with our lesson from 3.7, where we have a review over all the different functions, linear, absolute value, and quadratic, where we graph them, we discuss who their parent function is, domain range, how many roots, which means where we cross the x-axis, our ending behavior, which is new, as well as our increasing and decreasing intervals. So on 24, I have the absolute value of x minus 3 plus 4. Well, because I see this has absolute value bars, that means its parent function is, no surprise, absolute value. So let's graph using our vertex form. My vertex, because every absolute value function has a vertex, would be +3 for x, +4 for y. So we're going 3 right and up 1, 2, 3, 4, first dot. Okay, then I need the slope. My slope, I'm looking out in front of the bars. Nothing's there, so it's 1/1, up 1, right 1, and then mirrored on the left. So up 1, right 1, up 1, right 1. And then we go back to the vertex, go up 1, left 1, because it's a V. Okay, connect our points. Okay, domain. So we discussed this a lot of times. The domain of every absolute value function is all real numbers. We have left to right spread forever without interruption. We don't have any of that piecewise business going on here. Our range, we're looking for our lowest value, okay, or our highest value. This one had a lowest, a minimum, and our lowest y value was 4, and we're moving above 4. So this is for our range, all the y's such that y is greater than or equal to positive 4. Now roots mean how many times do we cross the x-axis? That's going to be a big deal next chapter. So here's my x-axis. Does my v ever pass through here, and will it ever? It doesn't. My vertex is above the x-axis and my arrows are going up. So on this, we have 0 roots. Now end behavior, it's what it's implying. How are my arrows ending? Are they ending up or are they ending down as we move from to the right and as we move to the left? So again, this is read as x approaches infinity is how that's read, which means as I move to the right. Because on the right side of the x-axis, we're getting more and more positive. That's positive infinity. Okay, the left side of the x-axis we discussed is negative infinity because we get more and more negative, but we can never reach it. So as we move to the right, okay, so I'm on this side over here, where's my arrow ending? It's ending up. So for y, which is shown by f of x, that's the same as y, that would be positive infinity for ending up. Now underneath that, we say as x approaches negative infinity. This means as we move to the left, where is f of x, or in other words, y headed, up or down? Y is also headed up as we're moving to the left, so it's headed towards positive infinity as well. Okay, so they match because both arrows end the same way, and again, this is ending behavior. Now, increasing and decreasing intervals. Okay, these are x values. Okay, for which x values are we increasing or having a positive slope? For which x values are we having a decreasing or negative slope? So I told you guys to start by finding your vertex, because remember our vertex is called a turning point. If we have a vertex, we're going to have both increasing and decreasing intervals. Okay, so we always read graphs left to right. That's like the big thing here. So find the left side of one of your arrows. Wherever that's at, that's where your little guy's starting. Now, is his elevation, is it increasing or decreasing? Or in other words, to get to the vertex, is he walking uphill or downhill? My guy has to walk downhill to get to the vertex, so he's decreasing. And for which x values is he decreasing? Well, we're trying to think. He's coming from left to right. What's the leftest he can get? And I made up that word. Yes, leftist. The leftist he could be from is coming from negative infinity. Because these are x values that I care about. Okay, where is our slope increasing and decreasing for these x values? Till the vertex, but I don't want the y value from the vertex like I usually do. I want the x value of the vertex. The x value of the vertex is 3. So from negative infinity to 3, we are decreasing. We'll write that here, and that's going to be negative infinity, comma, 3. He's walking downhill, in other words. Then we have to always start over at the vertex. So I'm kind of drawing him again. And from the vertex to the right forever, which will always be positive infinity, he's walking uphill. That means he's increasing. So from positive 3 for x to positive infinity, he is always increasing or going up. Okay, that's it. Okay, number 25, we have f of x equals negative 6/5 x plus 2. Now right here, this x that we have does not have a squared sign, does not have absolute value bars around it. This is a linear equation, which is going to be a line, linear. Okay, so when we graph these, we're thinking of how it compares to y equals mx plus b. The b value is 2. The b value is where you start on the y-axis. So we're starting at positive 2. That's my first dot. Negative 6/5 is my slope. It means to go down 6, right 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Plant a dot. I can go back to my starting point. I'm going to go up 1, 2, 3, 4, 5, 6, and left 5. Okay, so notice we do have a nice diagonal line. Okay, domain. Notice my arrows are ending in opposite directions all the way around here. We have left and right spread forever without interruption. My domain is all real numbers. My range. Okay, notice these are also ending in opposite directions. One side's going down, the other side's going up without interruption. So we would say our range is also all real numbers. How many roots do we have? How many times do we cross the x-axis? So if I move along the x-axis, you should be able to see very clearly that we only cross the x-axis one time. So we have one root. My ending behavior. How are my arrows ending as we move to the right and as we move to the left? Again, make a note. The right side of the x-axis is approaching positive infinity. The left side of the x-axis is getting more negative, so it's approaching negative infinity. So this piece right here, as x approaches infinity, means as we move to the right, where is y headed? Is it headed up or headed down? And we can see it's headed down. That would be negative infinity for y. As x approaches negative infinity, this means as we move to the left, where is y ending? Up or down? Well, here's negative infinity. I can see that arrow's ending up. So up for y is positive infinity. Now, notice this is a linear equation. It does not have a vertex. It does not turn around. Okay, so it is only ever going to be either increasing forever or decreasing forever. So start at the leftmost point of whatever arrow you've made, okay, or for your line, and that's where I'm putting my guy. Now, he's starting here. He has to move to the right. Notice he's always sliding downhill or walking downhill. It'd be more fun to slide, though, forever. To get lower, that means he is decreasing. Okay, he's decreasing forever, but for which values is he decreasing for x? Again, the leftest we can get is negative infinity. The rightest we can get is positive infinity. So again, decreasing forever. So from negative infinity to positive infinity for x, my slope is always going down. We never go up, so we do not have an increasing interval on this one. Okay, number 26, we have f of x equals negative x squared plus 8x minus 14. As soon as we see that we have x squared, and that's our highest exponent, we are dealing with a quadratic. Okay, that's our parent function. That means we're going to have a parabola. What kind of parabola? What's in front of x squared? That negative means arrows are going down. So we have more of a rainbow here. If I type in negative x squared plus 8x minus 14, I'm going to hit graph, and then I'm going to hit second graph, or you can be using Desmos to do this, but we're going to get our table of values. And then you're going on your vertex hunt. Okay, where is the middle of your parabola? Okay, what's going in the middle of your table? Now, if I'm scrolling down, I can see that for 2 for y, 2 is the only y value, that's 2. And then on either side of that 2 for y, there's 1s. So that's kind of how you'd be looking for on your graphing calculator, where we start having symmetry about 1 point. 4, 2 is going to be our vertex. And again, you could have used x equals negative b over 2a, which would have been negative 8 divided by 2 times negative 1, which does equal 4. Okay, that would be the x value of our vertex. Again, but using your graphing calculator, since you have them, is just way quicker. On either side of that, we're going to have 3, 2, and 1, 5, 6, and 7. So on either side, we are going down to 1, then negative 2, and then negative 7. Our values are getting lower like they should because we knew it was going down. So we're at 4 and positive 2, and then down to 1 on either side, and down to negative 2, and down to negative 7. Connect your points. Remember when the only thing you had to do was graph and not all this extra stuff? That was pretty cool. Okay, domain doesn't change. Our domain is going to stay all real numbers. We are spreading left to right forever. Okay, but our range, it's like the range for our absolute value. We're looking for a highest or lowest point. Our vertex is a maximum. It's our highest point, but what's the y value? Because range means y's. That's a positive 2. And everything is going under 2 or below 2. So our range is all the y's such that y will be less than or equal to positive 2. How many roots do we have? As we move across the x-axis, how many times does our graph cross? Twice. So 2 roots here. Ending behavior. Okay, where are arrows ending? So we have positive infinity on the right side of x, negative infinity on the left side. As x approaches infinity, as we move to the right, where is f of x, or in other words, y, ending? Okay, so on this side, we're ending down, and for y, that would be negative infinity. As x approaches negative infinity, so as we move to the left side, okay, over here, my arrow is also ending down at negative infinity. Both arrows end in the same direction. We do have a vertex here. Okay, if you have a vertex, we have a turning point, which means we have both increasing and decreasing intervals. So I'd like to find that value right here. What is the x value? We're not talking about y values. These are x intervals here. So the x value of our vertex is 4. That's what we're using. We're moving from left to right, and 4 is going to be kind of our turning point. So I know that some people are going to think that we have 2 decreasing intervals. We don't, because we're reading left to right. So I put my guide the leftest we can get, which is here where I've placed him. That's the left side, because he's now moving to the right. He's moving towards the vertex. To get to the vertex value, okay, for x, he has to go up to get there. He's increasing as he moves to the right. So that's my first increasing interval, and it's happening from negative infinity for x to positive 4 for x. Negative infinity to 4, he's walking uphill. He always starts over at the vertex, so my guy's starting here now, and at the top of the vertex, now he gets to slide downhill forever after that. But what x values is that? It's from 4 to the right forever, which is positive infinity. So 4 to infinity, he's going downhill. He has a slide. Whee! Fun. Okay, number 27, we have f of x equals x minus 4. Now look at your x. No absolute value bars and no squared. So this is just a line. It's linear. We have a starting y value. My b value, my y-intercept would be negative 4. 1, 2, 3, 4. I lost that right here. And then we have a slope of x, which means up 1, right 1. So here is our line. Beautiful. Linear equations are very quick to graph. It's why they're like the first ones we start with. They're the easiest. And it's done. Okay, the domain is still all real numbers. My range, we're moving bottom to top forever, so our range is still all real numbers. Every linear equation is. How many times will a linear equation cross the x-axis? 1 time. That's it, every time. How is our end behavior? Notice our arrows end in different directions, but this side will be positive infinity for x. This side would be representing negative infinity for x. So as x approaches infinity, as we move to the right, where is y headed, up or down? It's headed up, so that's positive infinity for y. As x approaches negative infinity, as we move to the left, okay, this side, where is our arrow ending? End behavior. It's ending going down, which represents negative infinity. Okay, now our increasing or decreasing intervals. Keep in mind, we do not have a vertex here. We have no turning point, so it's either going to be always increasing or always decreasing. Put your guy on the left side end of your arrow. Okay, now think, how is he moving? He's going uphill or increasing his elevation forever. He's always increasing. He's never decreasing. He's never going down. He has to walk uphill forever. Like I said, Greek mythology. I wonder what bad thing he did that he has to keep doing this forever and ever, like the guy holding the world on his back. So how do we say that? Again, it's x values here that we're describing it with. So from negative infinity for x, that's the leftest we can get, to positive infinity for x, that's the rightest we can get. He's always increasing. So we say negative infinity, comma, positive infinity. We are never decreasing for this one. Okay, our last problem, and I really wonder if anyone's ever going to watch this. But here we go, so much fun. We have negative 1/2 times x plus 1 all being squared. That squared automatically makes this quadratic. So we're having a parabola. Okay, I'm going to have a fat parabola that's going down. Because I have a negative sign, that's a reflection. 1/2 makes it fatter. So this is in vertex form. So I know where the center of my parabola will be. Looking at this, I take what's opposite of inside the parentheses with x. That would be negative 1. The y value is 0. Now if I type this into my calculator, when I can see that negative 1, 0 is my vertex, I have negative 1s for y on either side of that, but I don't want to, or negative 1/2, and I don't want to graph negative 1/2. I could, I just don't want to. But I can see at negative 3 for x, I get negative 2. And negative 4 gives a fraction for y, but negative 5 gives negative 8. So again, you can choose just to graph the whole value points. And I can see that positive 1 for x gives me negative 2 for y, and positive 3 for x gives me negative 8 for y. So let's graph these points, negative 1 and 0. We're going down to negative 2, but not on either side. We're moving outwards by 2. So 1 and negative 2, and negative 3, negative 2. So he's a little fat. It's okay. We're not going to judge. And negative 8 here and here. All right, our domain is going to stay all real numbers. If anybody misses out on the test, I'm going to cry. What's our range? Our range, we have a vertex that's a highest point. What's that y value? Because range means y's. That's 0. And my arrows are ending or are pointed downwards underneath that. So our range, we have y values for all y's such that y is less than or equal to 0. Now, how many roots do we have here? This one's a little bit different. As we're moving across the x-axis, notice we don't really ever cross through 2 points. But my vertex is resting on the x-axis. So this is how we get 1 root. Okay, our vertex is sitting on the x-axis. Let's talk about our end behavior. The right side of the x-axis is positive infinity. The left side is negative infinity. So as x approaches infinity, as we move to the right, where are we ending for y? It's ending down towards negative infinity. Okay, down here's negative infinity, up would be positive. As x approaches negative infinity, as we move to the left, where is y headed? It's also headed down towards negative infinity. Increasing and decreasing intervals, we do have a vertex. We have a turning point, so we have both increasing and decreasing intervals. Now, might be a good idea to label the x value of this because we don't want the y like we have used most of the time. The x value is negative 1. So remember, we're kind of going to be using all of these x values. Start your guy on the left-ended arrow. From left to right, from the left to the vertex, he has to walk uphill. So he's increasing from left to right. So that would be from negative infinity to negative 1 for x, he's increasing. Decreasing, he starts over at the vertex, and then he's going to slide downhill to the right forever, and the right forever for x is positive infinity. So from negative 1 to positive infinity, he's always decreasing. At this point, we've talked about it in class, you should notice one of your intervals should always start with negative infinity, one should always end with positive infinity, and the two numbers that you use should always be the same. Okay, that's always going to happen for these intervals for what we're doing so far. All right, good luck on your test. Don't choke.